Hello, CIS 4338 students. Professor Merchant here. So, in the update video, I showed you that we're working on Unit 103. And then of this content that's required in this unit, I'm going to create several videos to keep them short. There will be several. But I'm going to create videos based on these slides. So you may want to open up these slides, Normalization Basics, and then the normalization examples that's in a document format. You might want to open that as well, although those examples are somewhat embedded into the slides. Okay. Alright, so we're talking about relational databases, and that structure for storing data was invented or discovered or whatever you would, however you would describe that process that originated it in the early 1970s. So we were saving data before 1970, but you had to build a system from scratch, and you could define your own mechanisms for how the computer would store the data and what kind of methods you would have for retrieving it and so forth. But then, and at that time, memory, storage, and random access memory were very expensive, and they're not so expensive today, but because they were relatively expensive at that time, then you wanted to store data efficiently. And so an issue that arose was having the same pieces of information in lots of rows of the database, or lots of places in the database, because it wasn't necessarily rows and columns, wasn't how you conceptualized it. So anyway, the relational theory came about because they were trying to come up with the most efficient way to store data that would maximize the storage in terms of memory cost. And so this relational model is a conceptual model. Certainly the data isn't stored on disk in rows and columns. It's just a way to think about it. And then all the relational database management systems are built to work with those concepts and translate those concepts into actual storage locations and so forth. So the concept is that a relational database contains a number of tables, and each table consists of rows and columns. And a table represents an entity, and that's something within an organizational context, generally speaking. And then each column within the table represents a characteristic of the entity, or an attribute. And then every row is an instance of the entity. And again, this table concept with rows and columns, it's conceptual. It's a logical model. It's not physical. And again, here's the person who came up with relational theory, E.F. Codd. So a database is a structured set of data held in a computer usually. And the structure that you impose on the data doesn't have to be a relational model. Before the relational theory was developed, the relational model was emerging in practice, but it became formalized in the 70s with this research. So a relational database is a set of data that is structured conceptually as a collection of tables that represent entities. And the tables may or may not be related, but when you do have one table related to another, then there's mechanisms for establishing those relationships that are built into the systems, the database management systems. All the data in a column has to be of the same type, also in a relational model. Here's an example showing two different table entities, one representing a customer and the other one representing an order that the customer has placed. And so you see columns that represent the attributes. So the customer entity has a name, a street address, a city, a state, and a zip code. And an order entity has a customer and has items that they order, and quantities and unit costs and so forth. So, in your initial database design, usually you determine what data needs to be stored. And you do that by looking at the business needs and identifying the entities that need to be stored for the business and the business purposes. And there's other things that you might consider. Is the data going to have a lot of updates, inserts, and delete operations, or is it just going to be retrieved and viewed? Because those characteristics might impact the design and later on the implementation. So when you're doing this design process, what you're creating is a logical data model. And then when you turn it into a physical database design, that's the implementation process. And there's not necessarily a direct mapping from the logical model to the physical database design, because some of these other considerations that come into play can impact your physical design. And the application you're building can also influence the database design. What's the purpose of it? So one of your design goals when you're working on a database, building a database design, is to arrange the data so that retrieval and maintenance is as efficient as possible. And one way to achieve quote-unquote optimal data retrieval and maintenance is through normalizing, but there's also a process now called denormalizing, because in practice people found out that when you had a highly normalized design and you implemented it that way, that sometimes there are performance drawbacks to that. So now sometimes when you do the design, you go to a highly normalized design and then you do some denormalizing where you think it might impact your performance. Alright, so what is normalization? Well, the goal of normalization, the principle behind it, is to reduce data redundancy. And by doing that, you increase data integrity. And the reason is, if you have a piece of data that has to be repeated a number of times within your database, and then you have to change it, you have to update it, then you have to update it in several locations. So this existence of data in many locations led to issues of data integrity. So so normalization is a process that reduces duplication of data within tables. When you get through with the normalization process, the result is usually a design that includes more tables, and they're related to one another through keys that you set up. So if you read at various sources on the internet or otherwise about normalization, you will find the term repeating groups. And I see a lot of people talking about normalization and saying, oh, well, that isn't normalized because there are repeating groups. So I want to alert you that repeating groups of information in the rows of a table is a symptom of a denormalized structure, but it is not a characteristic of any of the normal forms. So I don't want you to use this term when you're saying something is in first normal form. I don't want you to say it's in first normal form because there's no repeating groups, because generally speaking that's never true. And it's a symptom. So it's not something that is included in the definitions. So here's a definition for normalization. It's a process. So it's not an end. It's not a goal, but it's a process, and it's a design process and an analysis process. You analyze a given schema and you look at functional dependencies that are there and the primary key structures, and then you do some restructuring in order to minimize redundancies and minimize insertion, deletion, and update anomalies. And that process now is what we call normalization. It's a design process and it's an analysis process. And you need extended information besides just your knowledge of databases. You need knowledge of the organization's information entities. You need knowledge of the attributes of those entities. You might need knowledge of the business processes being modeled by the data model, and you might need knowledge of the business rules. So good normalization improves data integrity by reducing data redundancy. It helps queries run efficiently, but it does increase complexity, so that the meaning behind the database schema sometimes is obscured by the increased complexity of the normalization process that the normalization process leads to. So you can have too much normalization, too many relationships, too many small tables with only a few columns. In that kind of environment, to retrieve one piece of information requires access to many tables through many joins. So these are some characteristics of a well-designed table. A well-designed table has a natural unique identifier, and the natural unique identifiers for a table are called candidate keys. And then you can have only one, but sometimes you can have more than one. And a candidate key can be the composite of several columns. It can be a combination of columns. It doesn't have to be a single column. And the candidate key can uniquely identify an instance or row of the entity. A well-designed table stores only information that directly relates to it. And you should avoid designs that require the same values to be stored in more than one place. So a unique identifier locates a specific row or instance through the identifier set. It can be one column or several columns. It has to enforce uniqueness in that no two rows would have the same set of values for the identifying set of columns. Sometimes in implementation, you can identify an entity or a table for which there is no candidate key, and so you can create something called a surrogate key, which is not a natural key, it's something you invented, and it's usually a number. But when you're going through the process of normalization and denormalization, the surrogate keys aren't there. Surrogate keys arise in implementation. They don't necessarily arise in design. So you may end up creating some surrogate keys, but they're not part of your analysis when you're doing normalization. Okay, I'm going to stop here, and then I'll come back and make the second video in which I'll talk about first normal form.